Hi, everyone. Thank you for joining our webinar today. My name is Julie Chen. I am going to be your facilitator, and with me is our speaker, Dr. Willie Hendrickson. So Willie is going to be talking to us about challenges and opportunities in spray drying. Willie is the founder and CEO of the Avika Group. Avika was founded in 1994 as a spinoff from 3M with just 3 people. And now it's grown into a big facility that does quite a bit of research, contract analysis. Willie is also very involved in International Fine Particle Institute, and he has co-authored over 20 technical papers, book chapters, and an inventor on 50 issue or apply for US patents. We will have a Q&A session at the end of Willie's talk. Without further ado, Willie, I'm going to go ahead and pass the ball to you.
All right. Well, thank you. Thank you for the introduction, and thank all of you for joining us here today. As Julie said, I'll be talking about the challenges and opportunities in spray drying. I'm going to give you just a one-slide overview of Avika, what we do, where I'm going to talk about the spray drying process, what it is, particle formation and types in spray drying applications, the economics of spray drying, and finally I'll give you a number of examples that will kind of tie this all together and come up with a conclusion at the end. And hopefully you all enjoy it. And so let's get going on this. As Julie said, we are a spinoff from 3M. We have 5 separate sites. They're not separate companies anymore. We currently have 200 employees, and we do primarily contract manufacturing, but as Julie said, we also do characterization work and we do R&D work, all in particle related areas. And over the years, I've given quite a few talks on different things like blending or agglomeration. And I will be doing another webinar, I believe in December or November. Julie will have to tell me when it is on jet milling. So I hope you join us on that one also. So let's talk about what spray drying is. Hopefully you all know what it is, but let me give you my view of what this is. Spray drying is, by definition, a drying of atomized droplets to form a free-flowing powder. That's the simple part of it, and there's lots of bits and pieces to it. I think we could probably go on for a week talking about what spray drying is, but I'll try to cram this all into 1 hour. The raw material characteristics, they can either be solutions or slurries. So, and typically they're going to be aqueous. Now, there are people that do spray drying of solvent-based systems. We don't do that, and it's hard to do that because of the explosive nature of when you're doing different solvents. But people do it all the time. I will be talking all about aqueous systems today. The feed that you're feeding to your dryer that you're going to atomize can be anywhere from 10 to 60%. This is primarily based on the viscosity. The higher the viscosity, the more difficult it is. So you're limited on the top end, and on the bottom end, you can obviously go down to 1% if you wanted, but the economics don't favor you very well. And I'll talk about that a little bit in the middle of the talk. What you get out of a spray dryer, the powder that you get is typically somewhere between 5 and 100 microns. Now you can push both of those limits. I've seen people get substantially larger than 100 microns, but in reality, the sweet spot for spray drying is in that 40 to 60 microns. That's typically what you get. The product itself, the powder itself, could be spheres. And I have to tell you, when I started in particle processing many years ago, my vision of spray drying was spheres, but it actually can be bubbles, raisin type structures, or even shards. And if you look at the SEM picture that I have to the left, you can see just about all of those structures in that one product. This is a product that we made, and I won't be talking about this specific one, but I thought it was just a great picture because it has a little bit of everything in it. Finally, the critical process parameters, there's probably a dozen more than just this one, but the ones that I'll be focusing on are inlet and outlet temperature, how that affects what you're doing. Basically, for commercial spray drying, we typically want to operate as high an outlet temperature as we possibly can. This helps us get faster yields out of faster throughput out of our dryer. We will look at the atomization method because we're trying to get that right droplet size to give us the best drying. And finally, we'll be looking at the feed rate and the airflow rate and the percent solids. I should have put that down on there. Those are all critical aspects of what we're doing when we're spray drying. Now, the uses of spray drying, this makes this one of these great technologies that fits just about everywhere. I've got a picture up here of some yeast particles that have been dried and then agglomerated. People use spray dryers for making catalysts, as shown by the cat cracking systems that are there. Pharmaceuticals, they'll spray dry the active ingredients or active ingredients with excipients to allow them then to make a tablet or a pill. Agricultural chemicals, ceramics, animal feed. I think we can go on and on and on. Lots of commercial chemicals, lots of dyes, pigments. These are all spray dried. This is a widely used technique, and the applications are almost endless. The types of dryers that people use, I've given you some examples here. This isn't the complete list, but if we start on the left side with the Buki spray dryer up at the top, this is a little teeny lab dryer. It's about 2 foot tall. If you're doing very, very small samples, this is a great piece of equipment to have. We don't find it useful for what we have. We actually start out with the mobile miner. The next one down, that's about a 3 foot diameter chamber as opposed to the 6-inch diameter chamber or the 8-inch diameter chamber on a Buki spray dryer. A mobile miner is many of the samples that we'll talk about today were made in a mobile miner. It's a great place to start. But then, once you've started to make these products, you need to scale up. And there's always a pilot dryer in between that mobile miner and your production unit. I just have a picture of a Nairo mobile miner. So instead of being 3 foot diameter, it's 5 foot in diameter. Instead of being 3 foot tall, it might be 10 foot tall. When you get into the big dryers, there's many different types, but the 2 types that I'm going to really talk about and give you an example of are box dryers. You see that up at the top. A box dryer is just exactly that. It's a stainless steel box. You atomize from the side, and you can see the high pressure atomizers that you typically use in this dryer. You spray across the chamber, the particles fall to the floor, and then they're swept up and scraped out of the system and then pneumatically conveyed to your packaging spot. Now, this is an interesting dryer. This was a dryer, one of the first commercial dryers that was developed was used for dairy processing. However, in today's world, people are using mostly tower dryers, as shown by that production bustle dryer or the production tower dryer. These dryers can be immense. As I talked about, the mobile miner might be, or the mobile miner might be 3 foot in diameter. A production bustle dryer or a production spray tower might be 30, 40, 50 feet in diameter and 100 or more feet tall. So these are huge, incredibly huge pieces of equipment. So we're going from being able to dry grams of product an hour to being able to dry multiple tons of product per hour. Now, as I said, some of the important aspects that I want to talk about today and really focus on are the atomization methods, because that droplet that you make is going to tell you a lot about the size of the product that you get, and at times can actually tell you about some of the shapes of the particles. So if you look on, just thinking about spray drying, if you look on the upper left-hand part of the screen and you look at that, this is a cross section of a dryer or a schematic of a dryer that has an atomization region and a drying region. And when you really look at that in the spray chamber, what you're looking at is how much capacity do you have in your dryer. Obviously, the bigger the dryer is, the bigger the drying region that you have, the bigger the particle that you can get. And once again, we'll talk about that a little bit later in our talk. If you look at the atomization, I want you to focus on the picture in the middle, the rotary atomization. I call it sub-parentheses Rayleigh breakup. This is a type of atomizer that's used on big dryers, and it's used a lot in food and ceramic types of drying. Basically, what you're doing is you're pouring liquid on a rapidly spinning disc. In this case, the disc might be going anywhere from 6,000 to 20,000 RPM. And if you have it really set up just perfectly, you'll get these nice ligaments that you see coming off off of the dryer. This is a liquid ligament that comes off, and then it breaks up in a very controlled fashion, and this is called Rayleigh breakup. If you can actually get your dryer to operate like this, you can get a very tight particle distribution. In fact, people, when they really work hard, they'll use a rotary atomizer to get that tight particle distribution. However, for the rest of us, we're typically using a spray nozzle, a single fluid spray nozzle is shown at the bottom. And what we have here is some pictures out of a report that Nasser Ashgriv reported in an IFPRI report, that he's looking at different atomization scenarios that occur as you increase the viscosity of the liquid. As you can see with water, he's making a lot of droplets in the system. As he goes to higher and higher viscosity, he starts forming more and more ligaments and filaments in the system. If you take this all the way to the far reaches, you could actually spray dry and get fibers out of a spray dryer. People typically don't do that. I mean, they're really looking to get a droplet out of this. But I thought this was really quite an interesting picture, because as you change your material, you can change the atomization, and which now can change the droplet size, which can change the drying of the particle that you get. Another atomization technique that's used, instead of using just a straight atomizing out of a single fluid nozzle, people will use a swirl cone. So they'll actually make a cone, and interestingly enough, it doesn't break up into droplets, it breaks up into sheets, which breaks it up into ligaments, and you can see how this all goes down here. Once again, you can get a lot of different mechanisms of breakup, which can also end up with a lot of different mechanisms or final particle form that you can get out of this. Understanding your atomization technique and picking the right atomization technique is absolutely critical. You can totally mess up your system by having something that's too viscous, or you can totally mess up your system and get too fine or too large of particles if you're using the wrong atomization technique. And many of the characteristics that we're looking at is, can we get that right particle size? Where particle size is important, the other part that's important is, what's your final form of the product that you get? This is a couple of diagram that came from another IFPRI paper done by Andrew Bailey, and he did an absolutely excellent job at looking at all the different types of particles that can be formed. This was a wonderful review that he did, and I kind of want to go through this step here, because I think this is very interesting. So if you start on the left side with your initial droplet, so the atomization is completed, we're now starting to dry the product. As you dry the product, the droplet is going to start to shrink, and eventually it's very likely that you'll actually form a skin around this particle. Now, depending on the temperature that you're drying, and depending on the viscosity, depending on the load of the particles, depending on the material, you can start to actually dry this to a nice solid sphere, as is shown up here up at the top. But that sphere, before it gets there, can break and form shards, and that's what this SCM picture over here on the upper left-hand corner is. This shards that form, but you can also see the droplets and the beads and the bubbles that were formed. But what happens when they break like this, you've heated it up enough that there's still liquid inside the system. It's not diffusing fast enough through, and will actually shatter the particle and make shards. By the same token, if you do it a little bit different and you have a material slightly different composition, you can actually form a hole in the middle. This is a vaporization hole that can now start collapsing and forming raisin type structures. And you can get these things all the time, and you'll see raisins as shown down here in the lower left hand corner. These are bubbles that formed, that then collapsed and formed kind of a shriveled up particle. In different situations, that particle can actually expand, and so you can expand the bubble, or you can actually form a nice bubble period. And if you take it to the extreme, as shown down here in the lower right hand corner, you can actually get some donuts or toroids out of the system. You know, this is not important if all you want to do is dry your product as fast as you can, provided you don't care about the density, you don't care about flowability, and you don't care whether the particles are breaking, turn it on and dry it as fast as you can. If this is critical for you, for dissolution, for powder flow, for can you fit it in a bag, you'll want to understand what's going on with this and control this to get the type of particle that you're looking for. Let me just give you another kind of view of what's going on with this mechanism, and we'll talk about this later in the talk. In a system, this is up in this upper left-hand corner, we're actually looking at the evaporation of a section of the droplet. As the particle is evaporating, it's shrinking, and two things are going on here. The particle is shrinking, and are we getting the solute, either the particles that are in solution or the molecules that are in a slurry or in solution, are they redistributing rapidly, or are they starting to collect at the edge here? Obviously, collecting at this edge is going to make that shell type of particle. If it collects a lot at the edge, you're going to get a hollow bubble. What we're actually looking at here is a dimensionless number called a Pecquelet number, where we're looking at the advection rate, the evaporation rate, versus the ability of the particles to realign themselves. If the Pecquelet number is high, obviously it's drying faster than you move the particles around, you'll form a skin. And this is shown by, once again, some pictures out of Bailey's review, where at a high temperature, you started to form that in a high Pecquelet number because it's evaporating very rapidly. You'll form spheres, or excuse me, bubbles. But at a low Pecquelet number, a low evaporation rate, you'll form solid spheres. Now, the reality is, in commercial processing, you hardly ever form spheres. And the reason for that is it's all about money, right? It's all about how fast that we can evaporate this material to get something out. And so industrially, we're going to be pushing this thing. We're going to be forming bubbles a lot. Well, let's just talk about the economics of spray drying. In general, when you're doing a big spray drying operation, you're gonna want to get as high a yield as you can possibly get, and 98 to 99% yield is something that happens with absolute regularity in large scale drying. The process parameters that you're looking at are the input solids, the drying rate, and from an economic standpoint, you want to get somewhere between $500 and $1,000 an hour out of your dryer, whether that's an internal charge that you have or the charge that somebody's going to charge you for drying it. Overhanging all of this is this incredibly large piece of equipment to do large scale processing that might cost anywhere from $10 to $50 million. So you want to get this thing to work as fast as you can, because you have an expensive piece of equipment. So you're going to dry fast, which means a high Pecquelet number, which means that you're going to get bubbles out of the system. The picture at the bottom of this screen is a picture of the bottom of one of our large dryers. This is about a 20-foot in diameter dryer, and it's about 80 foot tall. And schematically, I've just shown you where we have up here in the upper right-hand corner, where we're having the atomization go on at the top of the dryer, the drying in the bottom, and then we're collecting in a cyclone in this particular case. Cyclones, bag houses, other ways of collecting your product, any of them will work, but they better work well, otherwise you won't get the yield. So let's just take a look at this. We've got this big dryer, we need to fill it up, we need to get a lot of material through here. What does this really mean for us? So I'm doing an example here where we're having drying at about 2,000 kilograms of water per hour. If I only have a 1% solid solution on a 2,000 kilogram per hour dryer, I'm only going to get out 20 kilograms an hour. If I got to make $1,000, I'm going to charge somebody $50 a kilogram for that drying process. However, if I get up to 20 weight percent, I'm at 500 kilograms per hour on a dryer that I need to make $1,000 an hour on. I'm going to charge $2 a kilogram or $1 a pound for this. Obviously, if I can get it to go up higher and higher, I can get more out. It still costs me the same amount. Can I go with a high percentage solids? With ceramics, you can actually get up to 50 to 60% solids, maybe even 70% solids sometimes, and you can actually dry a lot of material with a smaller dryer. In food processing, you're typically operating in the 20 to 40% solids. So food processing, just from a, I've got this big capital piece of equipment, I'm going to need to charge more for that than not. Now, what I'm showing here is that this drying, as I go up, as I double in volume or percent solids, I actually go up more in output rate. And this is just because of the way the math and it all works out. But you'll see here that, you know, I truly want to operate as high a concentration I can, because I can get out the most product. I can have the lowest cost for my system. But, you know, this shows what happens with big changes, what happens in reality and small changes. So here I have a case. This is, once again, this is just a calculated system. If I have 19, 20, or 20% solids, and, you know, think about that. That's very likely to happen. You make up your material, or you receive material, and varying by 1% isn't a big deal. But look at the change that it makes on the drying kilograms per hour. Once again, this is at a 2,000 kilogram per hour evaporation rate. Going from 19 to 20%, I go up 31 kilograms an hour. If you just think about this, that might not, that's output product that theoretically that you could get out of your dryer. That might not seem a lot till you really start putting this over an entire year, where you're either operating at 80% uptime, 90% or 95% uptime. With 20% solids, you can go from 3.5 to 4.1 million kilograms of product coming out of your dryer, simply by how well you're maintaining and how much you're operating your dryer. But if you look at what happens if I'm only at 19% and 80% utilization during the year versus 21% and 95% utilization, it's about a 1.2 million kilogram per year production. At $2 a kilogram, that works out to $2.5 million more you can make simply by increasing your percent by 2% and operating your dryer as often as you can. Now, the reason that you might not be able to operate your dryer for 95% efficiency, and that's about as well as you can get, because you got to stop and repair it occasionally, and you got to fix things and the like. But if you have to stop and clean up your dryer, that might take 2 or 3 days. Once a month, you're at 90%, and twice a month, you're at 80%. So how you set this all up and how you run it means a big difference on how much material that you can actually get. Now, the other thing that could happen is that your dryer might not be operating at 2,000 pounds of water evaporation an hour. And so if we go back to that same 19, 20, and 21%, you can see that by by operating at higher efficiencies, we can get a substantial amount more of product coming out of this system, whether it's at 20%, 19, or 21%. It's, you know, around 50 kilograms an hour. And obviously, if we can do this at higher and longer, or higher and faster rates, we can actually maximize this. We can get almost 800,000 kilograms an hour or a year out of the system more than if we were operating at a higher rate versus a lower rate. So what causes the evaporation rate to change? And the answer is, do you have your dryer tuned up properly? Do you have any leaks in it? If you have an air leak, a dryer is operating at a negative pressure. If you're sucking cold air into your dryer, you're going to have a lower evaporation rate. If you're bringing in air that has a higher humidity, relative humidity, you are going to actually have a lower evaporation rate. So people really work hard to maintain their dryers, keep those leaks out of there, and they really want to operate in Arizona where the relative humidity is less. The final thing is yield, and this is a funny spot. I mean, when we assume 98% yield, if we have theoretically the ability to get 500 kilograms an hour out, we're really getting 490 out at a 98% yield. However, there's a little game that we play with ourselves. We calculate out what the yield is based on the percent solids that you could possibly get out of there, but in reality, there's always water left in your product. So even though you have 500 kilograms of dry product, you actually have the ability at 8% retained water to get 543 kilograms per hour out of the dryer. But we're only getting 490, and we're still calling that 98%. But my question here isn't how we calculate our percent yields. But my question is what happened to that other 53 kilograms I've lost? This is, approximately 10% of the product that's lost, and it goes into two places. Some of it goes down the drain, and when it goes down the drain because you're cleaning up or you've spilled a little liquid or whatever it is, you've lost that yield. The other part is I mentioned how you collect your product. If the product is not collected properly, if your cyclone or baghouse is not operating properly, you're not going to have an Oklahoma dust storm coming out of your dryer, but it can be pretty exciting when you have your collection not working. A, your yields aren't as high, and B, there's a lot of people mad that live around you, and you really don't want that. The reality is that if you control your process, if you don't have problems, if you're not washing it down the drain, if you're collecting it properly, you can have a much higher yield. I would like to collect that extra half a million pounds of product and save myself another $1 million. The overview on this thing is your water evaporation rate is going to depend on your relative humidity and your preventive maintenance, how good you're doing with that, and your operating time in the green. So if you can operate a lot, you can improve the economics of your dryer. If you can improve, you can have higher percent solids or higher yields, because once again, you're stopping it from sticking in your chamber and then losing that or having poor collection, or you're improving the percent solids, you're also going to have a better operating dryer. And because of this, because of the high cost of a dryer, because of the high cost of operating a dryer, we are always focusing on that. And what we are always doing is we're drying as fast as we can, which puts us back into we're going to make bubbles out of this. So let's take a look at some examples. How are we doing with how are we operating? Give you some view onto what's going on this whole system. So I'm going to talk about dryers and scaling up. I'm going to talk about some easy to dry materials that have some challenges with them. I'm going to talk about a hard to process material, and I'm going to finally talk about when your dryer's not operating right, what are the other explanations? What else can possibly be going on? So let's get into these examples. So scaling up of a new product. I mean, this is what we all do. We start in one of these mobile miners that I showed you. We're gonna scale it up and see how that goes, and then we're finally going to get to our big dryer. In this particular case, a customer came to us and asked us to dry a polymer for ag applications. And basically, we started out in our small dryer. They wanted about 60 microns, 68 microns, which is what they had from a competitive product. First test that we did, we got 19 microns. Oh, that's a little off of 68 microns, but we're in a small dryer. And remember, we've got a small atomization chamber and we've got a small drying part of the chamber. We should expect to have a smaller droplet size in order to get it to dry and not hit the walls. And we also should expect, if we go to a bigger dryer like we do when we go to our pilot dryer, we'll get a bigger particle size, which we did. We went from 19 to 45 microns. This is good. At this point, I have at the bottom here the HORIBA particle size distribution that we have from the competitor's product, and it was 68 microns. We have to now be able to tell our customer, does this make sense? Can we actually take this to a bigger dryer, and is it going to get to that 68 microns? Because it's still not flowing properly. Smaller particles are going to flow less well, and that's exactly what we were seeing. So if we can go to the larger dryer, can we think this is a valid step to take? We said yes. We said yes. We think that going to a larger dryer, we're going to get a larger particle size. Now we haven't done that yet, and our customer is still trying to decide whether they want to do it. But we think that just because you have to have smaller droplets because you have a smaller chamber size and a smaller dryer, we should expect to see bigger. This is what the lab dryer sample looks like. You'll see an SEM image up at the top that has an incredible number of small particles, and in fact is actually a solid particle. We have we must have had a lower Peclet number on this thing, and we actually ended up with solid particles, which is unusual. When we went to our larger pilot dryer, the particles were bigger, 45 microns, and you can actually see a couple indications of hollow particles. The dark spots on some of these particles indicate that there was a hole in the shell, which is a very good indication of a hollow sphere. And yeah, so we're getting to the right size. When we looked at the competitor's product, two things that we see here. Number one, there's even more bubbles, and you can actually see some broken bubbles that are kind of shard-like. The particles are bigger. We should expect it to be more of a flowing system. But also, if you'll notice in here, the particles aren't spherical. They're really some odd shapes in here. We think that this could either be because they're changing their system a little bit. They're maybe operating at a higher percent solids than we are, and so they have some elongation. Or these odd shaped particles are because there's an agglomeration process going on simultaneously to the spray drying process. This can be an agglomerating dryer. Now, having said all this, we think that we'll be able to actually make this particle size. It might still need to be agglomerated, and we're willing to talk about that and actually do that on a second step, at least for the test run, the production test run. But in the long term, we're going to actually maybe need to agglomerate in situ. But seeing this, understanding what's going on with the particle formation, with the droplet formation, with the drying, you can kind of see that yes, we can have a belief that this is something that we can scale up. What went wrong? Nothing. It's just that there's always tweaks that have to be made, and even in the proof of concept, there will need to be some adjustments. So let's look at another example. We had a case where somebody asked us to make a spherical powder out of a solid. They want us to resuspend this material and then spray dry it. Well, you can see the SEM here, not very spherical. It's the oddest particle we've ever seen. What we thought about this is, once again, going back to that advancing evaporation interface in drying, that these particles were so big that they couldn't get out of the way fast enough, and we ended up with these very odd particles. What we did is we took this material, we bead milled it, we got it going from 11 microns down to 2 microns, and we spray dried this material again. And lo and behold, we went from this odd shaped particle to nicely spherical particles. Once again, this really looks like a solid beaded particle. There's some indication here of some hollow particles, but not many. We got exactly what we wanted on this first try. This is what we like to see. Understanding what we're doing and trying to come up with the right solution is always the right thing to do. Now, one of the things that's happening on this next example is there's a lot of interest in the world right now in vegetable proteins. I like it. I think if we had more vegetable proteins, we'd have less global warming. But this is interesting. What's happening? What's interesting about this is we had 3 customers show up with 3 different proteins. We basically dried these all at about the same conditions, and we got the same structure out of it. You see that raisin structure on each one of those samples. So obviously, once again, drying at a fast rate, we formed that skin. But in this particular case, the skin was flexible enough as it cooled down, it collapsed into a raisin. What was interesting, and we don't really quite understand what happened here, is we got 3 different particle sizes out of this. A particle size of 64 and 55, I'm going to call that the same, and that's exactly what we expect to see in spray drying. But one material ended up with 92 microns, and this is a highly unusual particle size to get out of the dryer. They all have the same structure. They all have that skin formation collapsing. We're not really sure why this happened. One of the things that could have happened is that protein number 2 could have had a higher viscosity, even at the same percentage solids, which means that it's going to be a smaller or a larger droplet that's going to form, excuse me. That could be the reason. It could be that this material has a particular stretchiness that allowed it to balloon out farther, forming that, first the bubble and then the balloon as it did it, and then collapsed. We're not really sure, but this was a remarkable point for us to get this large particle size, same structure, that raisin structure, but a larger particle size. Sometimes you just don't know. You have to run the experiment and see. One of the things that we also do is we also do a lot of yeast. We do a lot of different yeast from different suppliers, from different types of yeast, different ways that it's handled beforehand. And it always bothered us is that even though we have yeast, and you could see the colorized version of an SEM of the yeast particles, they're all about the same size, 1 to 2 microns. And they all have the same structure that you see here, where there's a cell wall with a lot of proteins and other different materials on the inside. Why am I getting different sizes? Why am I getting different shapes? Why am I getting, why is it different? I have at the top of the slide a particle size analysis. It's 45, 55 microns. This is standard. We see this all the time. Obviously, we're agglomerating the yeast. That's exactly what we would see. But that the shape that we're going to see in just a second, and the flowability changes dramatically depending on the particle. What we think is going on is that these dried deactivated yeast, sometimes when you deactivate them and dry them, they break, and some of that lyses and some of the internal components come out. This yeast extract is sticky. There's a lot of protein in it. I think we think it's acting as a binder. Having different amounts of binder available or no binder available, it's going to give you different strengths. You're going to have attrition, you're going to have small particles, and small particles are always bad when you're looking at flowability. So here's 3 examples of 3 different yeasts that we did. Let's start out here on the right side. You can see nice bubbles that have formed. You can tell because of the holes, the black spots on these things. And if you look closely, you can actually see the individual yeast particles. Either on the low mag or the high mag, you can see it. If you look at the far left, it's that raisin type structure again. And how the heck can you get a raisin type structure when you have a lot of particles put together, unless there's a lot of lysine going on, there's a lot of this protein, and we know from a previous slides that protein is going to form this raisin-like structure. You can also see at the high mag version, you can see a lot of the individual yeast particles there. But we think that what's going on here is you have 2 different cases, very, very similar size, should dry the same, but because of this extra binder or protein in the system, you can actually control what's going on, and you can make all kinds of different particles with different flowability. The one in the middle is one that has a lot of protein in it because we specifically on purpose lysed that one. So it's everything all together, and in fact, it's actually forming that raisin-like structure, and harder to see the actual individual particles in there than in the one on the right. So once again, knowing the materials and knowing what you have and knowing how to control it can make all the difference in the world. Julie's always worried I'm going to talk too long, and so I've got 2 more examples to give you here. They're all about crystallization. One of the things that happens, and once again, going back to that article by Andrew Bailey on particle shape, is he reported some examples that a man named Vering reported in 2008 of spray drying sodium chloride. Aren't those pictures up at the upper right hand corner amazing? Sodium chloride crystals formed in a bubble formation that's around that particle. We were drying something, we didn't know about this at the time. We were drying sodium succinate, and we found out we had a nice drying, as seen in this bottom left-hand corner here. But when we looked at it broken open, we saw that it was an incredible crystal structure here. So we were forming bubbles, but we were also forming sodium succinate crystals. What was interesting about this to us is that when we left this material, we took it out of the dryer and put it on the lab bench just to take a look at it. When we came back, it had almost deliquesced. It picked up so much moisture. And what was going on here is that this material we formed the bubbles, we formed crystals, something that we hadn't seen before, but we've now seen it, other times. But that particle was falling in upon themselves, so we didn't form a stable particle in this particular case, and we had to handle this very, very carefully. We actually scaled this up. It worked out well, but boy, if you did it on a humid day, it was a real disaster. So this is my last full example here, and and once again, thank you all for listening. I want to talk about hard to dry materials, and in this particular case, hard to dry means they can pick up moisture and they're cohesive. And the one that we've spent a lot of time working on is sodium acetate. You basically are taking vinegar or acetic acid solutions, you're neutralizing them, with sodium hydroxide or whatever it is that you want. And what we found over the years, and this took us years to see this, is that different neutralization endpoints, whether it was below 7 or above 7, made a huge difference on how easy this product was to dry. In fact, what we found that the higher the pH that you went to, the better off it was, easier for us to dry. Still hard, it's still cohesive, it still picks up moisture. We also found that if we dried during the winter when relative humidity is lower, it was easier to dry. And that's not so surprising. I mean, people see this with lots of different materials, but this one showed up, not only was it easier to dry, but the flowability of this product at lower relative humidity was also important. Product stability, it was much more stable if we kept the storage temperature constant and the RH was low during drying. And in fact, the picture that I'm showing you here is what happens when this stuff was just stored. We had a 50-pound bag of this sodium acetate. We stored it for a month. It turned into a brick. This was as good as it could get. I mean, you could break this brick up, but it was agglomerating in the bag. And this is not unusual. Salt does this, sugar does this. But this one, we're not drying salt or sugar, we're drying this stuff. And how do we handle it? And what the heck was going on? So when we looked at these particles, they have the same particle size, whether it's high pH or low pH. But when we looked at the high pH, and it might be hard to see on this image, but we could see what appeared to be more crystal forms. So going back to that sodium succinate, sodium acetate also forms crystals when it dried. They form primarily solid spheres, and I'm still a little confused why it's solid and not bubbles. And when you look at the high mag, you can see this crystalline, these shards in there that seem to indicate that. When you look at the lower pH, there were still crystals in there. I mean, this thing is going on all the time, but it also has some amorphous nature. You don't see as much of that shards, and you see kind of a waxy looking particle. We think that these are amorphous particles. And what we're seeing here, the reason why at higher pH it's more stable is because the higher pH crystalline materials dissolve slower than amorphous materials. And this people see this all over the place, particularly in pharmaceuticals. They're always looking at this. In this particular case, that lower solubility, I mean, it's still very soluble, but that lower solubility just means that any moisture, whether it's in the dryer that it's picking up moisture, it can start to agglomerate. It can start to become cohesive. When you take it out of the dryer, the amorphous material is going to pick up moisture faster and start to block. So by understanding all of these sorts of things, you can actually get a good idea on how to control your dryer, what's going on, and then how to change the process parameters. Having said all that, what happens if you don't know what's going on? I just talked about moisture. The picture up at the top is a picture I took in Colombia. You can see the fog coming over the mountain, and it was just flowing like water. It was really quite an amazing picture to see and sight to see. As spray dryers, we hate water because it costs us energy to get rid of it. And water, usually high relative humidity, just causes problems. That one's an easy one to understand. Anecdotally, I had a friend of mine from another company talk about they had a process where they were spray drying, and they were drying their material, and they noticed that during the wintertime they had less of an issue with oxidation of their material, but in the summertime there was more of an issue. And when he got really into the depths of the details on this, the bigger problems occurred when there was a lightning storm close by. He actually was able to prove that small amounts of ozone, ppm parts of ozone, during the drying process caused a significant change in their product. Now, that's a hard one to imagine. I mean, water's an easy one to imagine. We like I said, we've seen it, but ppm parts of ozone can affect your spray drying process. I'm going to give you a last final one here that we saw with plasma torches in our building. We were spray drying in one of our plants, and somebody was plasma cutting in our shop, 100 feet away, 100 meters away, and behind 3 doors, and all of a sudden the metal detector goes off in our dryer. This is not what you want to hear. Something's broken, a bearing's broken, there's scraping going on. The metal detector detects it. It happened in about 10 bags. So, oh my God, this is really a bad situation. What happened is we analyzed this material, and we couldn't find any metal contamination in there. We looked at it under x-rays. We couldn't find any metal contamination. What we found out was ions that are produced in a plasma torch actually went through the air, entered the system, deposited on our product, and charge contamination is known to trigger a metal detector. This is an electrostatic contamination. It's edible, but because we could never prove there was no metal in it, we have to throw this away. These are the sorts of challenges that we see. So even on simple drying that we've done many times, somebody turned a plasma torch on, somebody had an electrical storm, the relative humidity rises. We think that we have it all under control and we understand it, and sometimes it's just not that way. So I'd like to summarize. Particle size and shape can be very important for you. Understanding the mechanisms of atomization, understanding the mechanisms of drying, and applying these can help you be a better spray drying person. The economics of drying commercially is that you're going to dry fast. You're going to probably get more bubbles than not. And understanding that and knowing how to challenge that and play with that is something that we can all do better. I'd like to point out, and I think I say this almost every time, whatever process you're doing in particle processing, the conditions in the materials can be absolutely critical. Small changes are everything in this business, and just be prepared for a surprise with even simple systems. I'd like to end with thanking you all for listening, and if you would like copies of those 2 papers, the Andrew Bailey or the National Astronaut paper, they're great papers. Please send me an email and I'll be happy to send you those papers. Thank you all for listening, and I think we still have time for some questions.
Yes, we do. Thank you, Willie. Thank you for the excellent talk. Let me go ahead and read the first question that kind of popped in the very beginning of your talk. What if we have ingredients in the wet mix, which is volatile at temperatures above 80 degrees C?
Well, that's a great question. So one of those volatile ingredients above 80 degrees C is acetic acid. So when you don't neutralize the fully, you will have 2 things that will happen. Some of that volatile component will be evaporated during spray drying. It absolutely has to happen, and we see that in spray drying of partially neutralized acetic acid. However, by the same token, there are people that by changing their conditions and handling it proper, I've actually seen samples where people have spray dried alcohol, and alcohol obviously is a boiling point less than 80 degrees, and they actually were able to encapsulate alcohol. It's a great question that person is asking. You would truly expect most of that solvent or that low vapor or evaporation material to go away, but people have figured out how to keep it in there if that's what you want. But typically it's just going to go.
Thank you. And the follow-up question is, what is the acceptable particle size distribution of dispersions in the wet mix for spray drying? And part 2, also, what is the maximum possible viscosity?
Both good questions. So I answered one of those in one of the examples I had there. If your particle size was too big, you're going to get some funny looking particles. So you might, typically I think people want to be less than 10 microns. But I've seen people spray dry fibers or needles. You just get very funny looking particles because you'll end up with your binder holding a bunch of needles together, or your binder holding bigger particles together. You can get by with it. And once again, it's changing those parameters. I guess I'd have to see what you're actually talking about, but you do it, but sometimes you get some odd results like I showed in that one example. With respect to viscosity, typically what people are talking about is, less than 200, absolutely less than 1,000 centipoise. But having said that, there's lots of tricks that people play. Different atomization techniques can allow you to go to higher viscosities. I've actually seen reports where people have, and actually on a commercial basis, I've seen people spray dry things that are in the 10,000 to 20,000 centipoise, but that's an incredibly special atomizer. And if you try to put too high a viscosity through your dryer, you'll make cotton candy is what you'll make. So typically the answer is less than 200 centipoise. You can work with that pretty easily, but there's exceptions that you can get higher if you need to.
Thank you. Next question, how is geometric similarity important for scale up?
For scale up? Wow. Something, I don't know the answer to that question. I'm not going to try to BS on this one. I don't know. That's absolutely a great question. I think people like to have, go from a tower dryer to a tower dryer to a tower dryer. But I think, what I was trying to show today is that knowing the Peclet number and knowing the time that you have in your dryer, I think you can get very similar products out of systems that are not similar. But I think you would be changing your parameters a lot in order to tweak it into what you want. But it's a great question. It's a very hard question. It's a good question.
Speaking of Peclet number, how do you reduce the Peclet number so that their particles are solid and not hollow?
Well, in that one example that I showed, the example from Andrew Bailey's talk, what they did is they just lowered the drying temperature, which means that, think about what that means. If I lower my drying temperature, it means it takes longer to dry that droplet. That will give you a nice solid sphere, but you're going to have a very tall tower if you lower it too much. So I think the other way that you can do that, lowering the evaporation rate, that's one way of lowering that Peclet number. The other way of doing it is to make it so the particles or the solute molecules can move around. So there's a viscosity issue. Higher viscosity is going to give you a higher Peclet number. Excuse me, yes, a higher Peclet number. Higher viscosity is going to give you a lower Peclet number. No, I'm confused. Let me just leave it at that. Sorry.
No problem. I think this is a good time for me to kind of share that there are some questions that are really hard to answer without more context. So feel free to just write to us at labinfo@horiba.com, and we'll be sure to forward your questions to Willie and follow up with you. We have time probably for 2 more questions. Let me go ahead and read that, and I want to honor your time, Willie. So, what are the main challenges for spray drying high fat ingredients? And is there a maximum % acceptable?
So people do spray drying of high fat ingredients. The great example of that is non-dairy coffee creamer. So what you're doing is you're emulsifying fat and water and then adding a water soluble binder. You have very small droplets. You dry the material. You end up with a nice bead. Typically, one of the challenges that happens is you need to cool that product after it gets out of the dryer, because there's a potential for a phase transition in the fat that will actually cause the product to get sticky and form a block. So one challenge is cooling that product rapidly. So people that dry non-dairy coffee creamers, which are high fat systems, they will always have a fluid bed cooler afterwards. The second thing that happens, you know, from a standpoint is if you put too much fat in the system, you can start to get an unstable product. So typically, you know, drying fats in a spray dryer, you're typically in that 40 to 50% and occasionally up to 60%. And beyond that, it's very difficult. You just get a too sticky of a product to get out of your dryer.
Last question. When you have high relative humidity, instead of slowing down the flow feed rate, the operator tends to increase inlet temperature, but this can cause problems. So, are there any other things that can be done to adjust the spray drying process?
So the best thing that, and many people do this, is they condition the air beforehand. So they'll actually put a dryer, an air dryer on the air that's coming into the system. So there's numbers of ways to do this. Obviously, you can just cool the air down so you condense out that extra moisture, and then you have to heat it up again. That's not the preferred way. But there's solid phase absorbents that people have that you can actually capture the water in things like zeolites or silicas, and it pulls it out of the system, and then they heat up the absorbent and they regenerate it. That's a very common thing to do, and in fact, that's probably the best way to do it. You know, a really good dryer will have a conditioner on the front end of it to remove that moisture and improve your drying consistency. Better than raising the temperature.
Thank you. And I have to insert this question. What is the best analytical equipment to use to look at quality of spray dried emulsions? And this is coming from our audience.
Spray dried emulsions?
Yes.
Well, it's you know what we've done with that. It's always particle size, and it's droplet of that emulsion. So the best spray dried materials have a droplet size. The oil part of the emulsion will have a droplet size of less than 1 micron, and preferably even less than a half a micron. And so if you're really going to challenge how good your spray dried product is, first start out with checking your emulsion droplet size, the oil droplet size. And so typically you're into now quasi-elastic light scattering type or dynamic light scattering types of systems. We've used that to qualify our emulsions before they go to spray drying. That's what I would definitely use.
So please get in touch with us. That's when HORIBA particle group comes in. But Willie, thank you so much for another amazing talk. Your next talk is going to be in December 6th. You can follow us on LinkedIn by typing in Particle Characterization Group. On behalf of HORIBA Particle Characterization Group, thank you, Willie, and thank you, everyone. We'll see you next time.
Thanks, everybody.
Thanks, Willie. Bye now.